This is Dominic Giambo from Wheatstone, who's going to be talking about some of the practical aspects of working with AES67. So take it away, Dominic.
Okay. My name's Dominic Giambo. I'm a development engineer with Wheatstone. I'm going to talk about things that we've learned by implementing and deploying AES67 and ST211030 in a test environment and what we've learned from that process. So what is AES67? It's a layer 3 protocol suite used to transmit audio. It was ratified in 2013 by AES, and everybody is beginning to use it. There's hundreds of audio devices that support it now, and hundreds more in development. So pretty much every broadcast studio will have this technology embedded in it and enable people to interoperate between different AOIP networks. Why do we need it? Well, it's the standard that's being used for SMPTE 211030. Again, it's supported by most of the major AOIP systems, and it's going to be key to transitioning your workflow for audio and video, integrating that all together in order to have a cohesive system. It's eventually going to be in every broadcast plant. What are the requirements of 2110.30 specifically? So 2110.30 is using AES67, but it has some special restrictions. It requires 48 kilohertz sampling for all devices. It requires a 1 millisecond packet time. Between one and 8 channels per stream needs to be supported. It also, we'll talk later about PTP, but it requires that you are able to place your device in a slave-only mode where it will not source a clock, just to prevent multiple PTP masters from existing. Simplifies the architecture by having only a single PTP clock, or maybe two, one for a backup, one for primary. The media clock offset for SMTP SMPTE must be 0, which is not for AES67. It doesn't require a 0 offset. SMPTE does require a 0 offset, which has to do with the timing that's present in the RTP packets. The media profile called out for PTP is this profile here, this 2059-2 for 2110, which is a rate of 4 announced messages per second. So what are we trying to accomplish? Well, we have a whole network of audio routers and consoles and control systems. All of that we call WheatNet IP, and that's our system. But how do you use that with other vendors? If you're, for instance, if you're trying to receive data from a Dante device, that maybe there's microphones at a remote site, or maybe there's some playout speakers at a remote site that you need to access. You can still use the network that you're used to, with whatever network that may be, but use AES67 to get to those other devices. And that's kind of what we're trying to do here. So what did we do, and where are we coming from with some of the things we learned? Well, we assembled a network of over 160 different devices. These were console surfaces. There was 62 blades, 100 software blades, which were either PC drivers or blades running as simulators, and three different automation systems, as well as Genelec speakers, Ward Beck equipment, Dante equipment, Axion X nodes, and switches from both Cisco and Dell. We cabled all this together. It took about 2 days just to cable all the equipment together, and basically ran an audio chain that originated, what we call blade 1, and went all the way through the entire system, including those AES67 devices. So this was a very artificial scenario where you're passing audio through every single device, creating a large chain. Kind of the worst case that you would never do that in a real studio, but if you lose any connections or there's any kind of audio artifacts anywhere through the chain, you'll see that. So that's why we set it up this way. And as we did that, we learned some things from it. So AES67 uses the IEEE 1588 PTP clocking. Our system originally used metronomes to clock, which metronomes are sent every 5 milliseconds in our system, and those sync the PLLs to enable so that you don't have clicks and pops in the audio. So that's what we did originally, and other AOIP vendors have done similar things. Everybody had their own kind of standard. PTP is being used by AES67 to sort of standardize on a clocking mechanism. And so we've changed our blades to support PTP, as other vendors have done with their devices. And this is basically how it works. You have some sort of GPS sync or clock, a good clock going into a PTP master. Those are being distributed by your switches. In this diagram, you can see PTP switches, but due to the requirements, we don't require sub-microsecond timing for audio. So you don't typically need PTP-capable switches. You can just use regular switches in most networks. It won't correct for the queuing delays present in those switches, but that just means you can't achieve sub-microsecond accuracy, which generally isn't required. So we'll go to the next slide here. Again, precise timing, better than 1 microsecond, but we don't really require that. We did find during this experiment that the PTP devices found in most AOIP gear that built in just are not good enough to provide the timing necessary for a large system. We really recommend that you use a dedicated PTP clock just so that you have very accurate timing. Many of the AOIP devices that source PTP clocks are just not accurate enough for good audio quality. They may be accurate for a short period of time, but over running for a while, you begin to experience issues. So we recommend that you use a dedicated PTP clock. And that's what we state here. Really want a specialized PTP master clock. The packet structure is called out by AES67, and the devices have to agree on the header and payload information, which is why it's part of the standard. So the packet structure that we were using, that we still use in most of our network, we use 1/4 millisecond packets. So we have the UDP header, which just includes the standard, source port, destination port, all the things that the regular UDP header would comprise. And then you have the RTP header, which gives you the timestamp that you're using that's based off of the PTP time. This allows you to know when this packet was generated and synchronize it play out. There's also a sequence number in the packet that's useful in case you're in a network where there are out of order packets. They can be reordered at the receive side, as well as telling you whether there's any packet loss in the network. You'll see discontinuity in the sequence number. So the way we do it with a 1/4 millisecond is just 12 stereo samples per left-right interleaved, and then AES67 calls out a 1 millisecond packet. So we now have 1 millisecond support, which again, it's the same header, same UDP, RTP header, only now you have 48 stereo audio samples in that packet, the same left-right interleaved. So this is the most commonly supported packet in AES67, and support in SMPTE you must have 1 millisecond support. So one other thing we noticed is that many devices, SMPTE requires 48 kilohertz support, and many of the devices that support AES67 actually don't support 44.1. Some do, but some don't, so that your best bet is to set it to 48 for now, unless you know all your devices do support 44.1. So for configuring, it's at this moment, without discovery mechanisms, which are coming with NMOS and other standards being developed, it's very manual in terms of setup. You need to specify a specific multicast address for every stream on the network. Some devices automatically allocate in some fashion or another, and you need to use the device's scheme along with a map, which I'll kind of show you to do that. And it also, AES67 specifies a standard UDP port, which is 5004. Our system uses 50,100 as its standard, but it can be changed, and we can receive or transmit to any port. So that was a change that was brought about by AES67. Again, discovery and control. AES67 just specifies streaming parameters. It doesn't manage those. It doesn't give you any way of making a connection short of going to a device and actually setting up a stream to receive, versus our system, which is typically using a graphical user interface. We have taken steps to integrate some features of control, which I'll go over later. But eventually we'll have NMOS, and we'll have something like AES, possibly AES70, and other control schemes that are being worked on now. We do have Sdp to provide those parameters and allow you to enter them in an easy way. Some devices support direct entry of Sdp. Other devices, you have to pick the Sdp apart to enter the parameters needed. So how do you map out the multicast addresses if you're going to use AES67? Well, it depends. It depends on the devices you're using. For instance, our blades, they use a certain multicast address range. The multicast address range can be modified, and it's essentially a contiguous range. So the way that we set up this network, we used a range for the WheatNet IP blades, and then we manually programmed multicast addresses for other devices on the network, other AES67 devices. In this case, this was an Axia X node with 4 sources that were running at 1 millisecond. So what you need to do is you isolate the address ranges for each of the AOIP systems you're going to be using. Certain device, like I said, some devices have certain ranges, like the blades that they want to operate in. Those ranges can be moved around to fit other devices in. Something like Dante, for a while you could change the XXX octet, but the YYY and the ZZZ would be automatically generated. So you'd have to play with getting the multicast addresses you wanted, so there was no overlap. If there's overlap, you're going to hear stream overlap, so we don't want that. So the other thing we just to note is that unless you do some higher level routing, multicast doesn't cross subnet boundaries, so you want all your devices within one subnet. Certainly, you can use routers to provide routing to multicast, but it's not something you're just going to be able to plug in and see immediately without doing some configuration. So how do you go about configuring this stuff? It depends. It's different. You use the vendor's tools. Our tool is Navigator. Um, when we set this up, you can see that there's a set of laser. Oh, so I can't see it on the screen. So currently we have the clocking mechanism. Instead of using Wheatstone IP metronomes, we're using AES67 PTP. When you do that, the blades detect PTP's present, and you get this green status, and you also get the GMID of the clock master of that PTP clock, and that way you know that the blades are synced to PTP, and that should work with any AES67 devices. At that point, you can then go and look at the blade, and in this case, our blades provide their multicast addresses in a table and various other places. The table's the easiest to view. So you can find what destination, if you have a destination AES67 device, you can put the multicast address and other parameters necessary directly into that device. Also, you can right-click on the signal and it'll generate an Sdp file if your AES67 device supports importing Sdp. So at this point, we had AES67 devices that did not support quarter millisecond, so we needed to enable 1 millisecond support. That simply switches the blade to use a larger buffer for packets so that it can support the 1 millisecond audio packets. It allows us to keep the rest of the system running at quarter millisecond, and then you can isolate the higher latency paths to only devices that only support those higher latency connections. This is showing that we've added a AES67 device. We allow you to add devices so that you can manage them within the Navigator GUI. And once you've added a device, you can then also add sources to that device. In this page, we're showing configuring an X node. This is the web interface of an X node. So in here, we've manually programmed in multicast addresses that are outside of our system range for multicast addresses so that they won't conflict with any of our sources. And we're set to low latency stereo with 1 millisecond. And this is just the port number. Here we're testing receiving from multiple ports. So 2 of these streams are set to 5100. 2 of them are set to the AES67 standard port of 5004. Once we did that, we could create sources in Wheatstone IP that represent these X node streams. So here you'll see we're editing the multicast address of the source to match this 240.100 is what we have here, and then we packet rate of 1 millisecond, the port of 5100, the payload type, the RTP payload type of 100. So once that was done, we had 4 X node sources, and we did the same thing for the other AES67 devices. And once we have the sources in the system, they persist and they're stored in the blades so that upon reboot, these sources are remembered. At this point, you can now use the cross point to connect those sources to any WheatNet destinations present, and the blades will transparently handle the packet rate conversions if needed. So if you connect it to any source in the system, or any destination in the system, it will transform that destination to be able to receive either 1 or quarter or 5 milliseconds, whatever is configured. It handles that automatically. So a little bit about Sdp files. Again, you can get an Sdp file. This is Navigator showing an Sdp file for one of our blade sources. The SDP file includes the source name, some information about the source, the audio payload type. This RTP map gives us the payload type, which essentially tells us what format the audio is in. 24-bit interleaved 48 kilohertz 2-channel in this case. And the packet time for this signal is a 1/4 millisecond. And we're just showing here that we are using a direct media offset. There's no offset, it's 0. So that is what you need for SMPTE. Over here we have a Dante file, same type of thing. You have all kinds of information. They're using 97 as their payload type, but the same format, so that when we get 97 in a packet, we know that that format is 24-bit, 48 kilohertz 2-channel. So these files, some devices will directly take these files and be able to import this data and create sources or destinations from that. So kind of in closing, what we learned from this experiment, I'll go back a little bit. When we did this, after everything was put together, we ran the system through about 160 different reboots. Some of it was automated, where we were using tools to monitor the audio coming out the end of the audio chain. Others, we were sitting there listening to the audio. After 160 reboots, we never lost any audio. There was no corruption, anything like that. So this system works very well. With AES6, we didn't lose audio on any of the AES67 devices. There were no clicks and pops. Everything worked cleanly. The main thing to keep in mind, again, we originally tried using some of the AOIP devices as master clocks, and we found that there were clicks and pops in the audio. It just wasn't accurate enough to maintain synchronization. That may change in the future, and certainly some devices could be better than others, but if you use a dedicated PTP clock, you avoid that. And obviously you need to ensure they're all on the same subnet unless you've done additional routing to be able to route multicast between subnets. You configure the desired multicast addresses, the ports, the packet timings, and the payload types for those streams, and then you configure the destinations to receive the streams that you want to receive. Or in the case of the blade, you simply make a cross point and it will provide the information needed to the destination.
Thank you very much.
Thank you.
All right, really appreciate it.